Well, good morning, everyone. Welcome to EasyPower's Thursday webinar. And today's topic is Advanced Harmonics. And let's call this Advanced Harmonics number 1 because I can see easily I could probably do a second one on some other advanced topics. And my name is Chris Duffey. I'm the principal engineer here at EasyPower. So similar to my previous presentations, I have a set of slides I'm going to go over, and then we'll look at some examples at the end using the software. So let's get running with the slides here. All right, so what we're going to look at today in this webinar are several advanced topics in harmonic analysis, and they include transformer derating, and we're going to be looking at the C57-110 standard, transformer K-factor via UL, harmonic losses, TIF and IT Product, Harmonic Bar Charts, which is a really useful feature when you're looking at spectral content, SinglePoint Injection method, and the all-source current flow method, which are two analysis methods inside EasyPower that let you do some kind of specialty looking at what might be happening at a particular frequency in your system while you're modeling it. And like I said, we'll review these slides on each topic and then look at some actual applications with an EasyPower example. So transformer derating is specified and documented in IEEE standard C57-110. And the basic equation is here, and there's a lot of text in that standard. And basically it comes down to this, and that is you want to determine how much current you can really put through the transformer, how much RMS current, versus what the rated current of the transformer is. And a couple of these terms I'll explain on the next slide. But if you actually wanted to do this yourself, if you had the harmonic currents, for instance here in amperes, you could actually perform this calculation or a hand calculation on the side and validate that, yes, EasyPower is pretty much doing the same thing that's in this equation. And as I noted, a couple of values I want to mention here are the LL value. That's the total load losses at rated condition of the transformer. And the winding rated losses are here in this item called P winding rated. And then this last term are the eddy current rated losses. And these are the three main loss figures that are incorporated in the C57-110 standard. Of course, we know there are many other losses that are incurred in a transformer, but they wind up being a fairly insignificant portion. We have stray losses in components on the inside. There's a clamping mechanism that clamps the core together. There are some losses that are in there as well. But when it comes to harmonic derating, basically we're going to include these two components, the winding rated losses and the eddy current rated losses. And what we find is if you go through a derivation of the derating equation in C57-110, you'll find that the eddy current losses basically end up being somewhere around, typically, I would say 2 to 15% of the total losses. And so that's the reason why we have kind of an odd per unitizing method here. And in the standard, what they do is they per unitize the equation by the winding rated losses. So that's why this value is 1 here. So knowing that, and knowing that a typical value for the per unit form of the eddy current rated losses is about 15% on this per unitizing basis, the equation becomes this one here at the bottom. Now, we allow you to put in any value of PECR per unit on the inside of the transformer dialog. So if you go to the transformer dialog under the harmonics tab, you'll see where you can enter this value that's specific to your transformer. If you don't know anything, then a PECR per unit value of 0.15 or 15% is a rather conservative number. I've seen other transformers on the market that have a significantly lower value, and this will definitely decrease the amount of losses on the inside of the transformer, which will make your derating factor go up. So the derating factor is going to be 1 or 100% if we can put 100% load through the transformer, and this number is going to drop. You're going to find this number dropping in terms of what you can put through it. And you know, I like to refer to it as a fundamental loading. I know it's RMS, but when you calculate the RMS value of the fundamental with all of the harmonic currents, what you'll find is that the RMS is pretty much equal to the fundamental, because the harmonic currents are typically a fairly small value once you do the square root of the sum of the squares. So this derating factor is pretty much an indication of how much fundamental loading you can put through a transformer with a given amount of harmonic current. I just saw a note here that the sound is low. I've turned it up a little bit. Tell me again if it's not loud enough for you. And I also just jumped a little bit closer to the microphone. So let's go to our next slide here. And we could go on a big, long, drawn-out discussion of the C57-110 and the derating. But let's just consider these main uses instead of going into that big discussion. The basic use of it is to determine RMS current that we can have with the harmonics. Or the way I like to look at it is kind of a fundamental loading that we can incur on the transformer with those harmonic currents being around. The reason why I include the RMS current there in that note is just because that's how the derating equation is formulated. And so I just want to make sure that we specifically note that. We also want to prove out overheating and loading safety margins on transformers. So this gives us an excellent indication, number one, if we have a transformer overheating condition, and it also allows us to evaluate prior to installing a transformer how we may want to possibly size it, make it slightly larger, for instance, so that it can handle the amount of both fundamental loading and harmonic loading. Now, let's jump to K factor, because these two are, well, they're kind of related. Let's put it like that. In reality, K factor, which is created by Underwriters Laboratory, is a transformer nameplate harmonic capability figure of merit. That's a kind of a big title there, but that's how I like to term it. It's a figure of merit that you put on a nameplate. Now, interestingly, it has no relation to the value of K in the C57-110 standard. Okay? So there's this value of K in the standard, and it has nothing to do with the equation, the summing of harmonic current squared times the harmonic squared. And so just understand that. If you go looking in the standard and you find K, it has no relation, okay? It's a UL creation that unfortunately does not incorporate C57-110 methods at all, really. And even though it kind of has a resemblance to it, and we'll see that here on the next slide. And for proper application, it's my opinion, this is my opinion, and also of several others in the industry that I know, that it really necessitates you producing what's called a K-duty, or performing a K-duty method calculation. And I'll explain that. Now, the UL equation is shown here. And you're, again, summing the harmonic currents squared times the harmonic squared, which is really, if you look closely, you go back here, that's the component that really deals with the eddy current losses here. This term is actually mostly from the eddy current losses. If you go back to the original formulation for your derating factor, that's what this component is. So we can see this relationship between the two. And so what we do is we sum those up and we divide them by I squared of the rating. Now, unfortunately, if you actually try to apply this in software, which I've done, what you'll find is it really doesn't work very well if you have a fundamental current that is 0 or maybe half loaded or 20% loaded. You'll find that this doesn't produce a correct number. So we've modified this so that if you have a 0 loading, what will happen is you'll get a K factor of 1. And in reality, you should never have a K factor that's less than 1, right? It's 1 or greater. 1 means you have the, it's basically fundamental rated. You can put fundamental current up to its rating, you're all good. A K factor that's higher than 1 means you can, on top of that, you can put harmonic currents through the transformer as well. Now, we really can't say how much harmonic current will a K-rated transformer allow. You can kind of do this, but basically there's an infinite number of possibilities. Because if you look at the way you calculate K factor, you sum up the harmonic currents, you square them, you square it for each harmonic, you multiply it by the harmonic number squared, 1, 2, 3, 4, 5, etc., and then you sum all those. So basically, you're trying to go backwards. You're going backwards from a number, like K factor of 4 or something. And you're trying to tell me, well, which harmonics can I have and how much of them can I have? And you really don't know because it can be any accumulation to produce a number of 4. So I recommend a method where we say, what's the K duty of my load? And thus, when we calculate the K duty, we can determine what transformer K rating we need. It's kind of like rating breakers. You calculated a current duty, then you compare it against the breaker rating, the current rating of the breaker, whether it's the momentary or the interrupting value. Let's do that similar for K factor. Let's look at our harmonic loading. Let's calculate a duty, a K duty. That's what is being produced by its flowing through that transformer and going through the K factor equation. And then we compare that against what type of a K rating we should need. So if we calculate a K duty of 2.38, we know we'd better have a transformer with a K rating that's higher than 2.38. All right, continuing. Harmonic losses. Now, this is pretty simple. What we do is at each harmonic, we're treating each one individually, each network for each harmonic frequency in an individual calculation. So for each network calculation at the individual frequency, we will calculate the KW and KVAR losses in components at that one frequency, like 300 hertz or the 5th harmonic. We'll calculate a value there. 7th, we'll calculate a value there. And what we'll do is we'll accumulate them into a total loss figure. And this is correct because of a number of things that we use in network computations, superposition, a number of these principles that allow us to look at each frequency individually. And it also has to do with inductance, capacitance, and resistance being linear components. And that is, we're assuming they're not changing. Inductance isn't changing. Now, the reactive the inductive reactance may be changing, going up and down with frequency, but the L, the actual inductance, we're assuming is fixed, and the same with the capacitance. That allows us to just sum the losses in a very simple method. Now, the harmonic losses add to the fundamental. So the fundamental is really coming from the power flow. If you have the default option in EasyPower checked, that says use fundamental values from power flow. So with that checked, given you have a valid power flow, it'll take the losses from fundamental losses from power flow and then add on the harmonic losses calculated in the harmonics module. So in reality, when you're running harmonics and you have power flow, they're running together. Now consider these comments. To date, and I've got a lot of background on this, to date, the harmonic losses, though claimed, in most cases are not a cause to install equipment to reduce the energy charge. I've done a ton of test cases looking at highly distorted systems, lots of harmonic currents flowing through transformers, and in reality, the additional losses, the harmonic losses, are fairly small. And you would be you'd have to have a really terribly distorted system to like a major resonance or something going on all the time. you'd have to have something like that to actually to where when you perform a mitigation and you want to say, we're going to pay for that mitigation by the savings, the energy savings from the harmonic losses that we're saving, you're probably looking 5 to 10 years, maybe even longer. That's my experience. There are some rare equations, not equations, there are some rare times, 0.3 here on the slide. There are some places where there's third harmonic neutral currents and other, and like resonant conditions, where losses are very high, and when you mitigate, you're saving a significant amount of money. But in most cases, that's really not true. You're saving maybe 1%, maybe 2%, maybe 3% in transformers. That's where you get most of your savings, are probably in transformers. But just know that. And also, you know, if you're going to consider harmonic losses for energy savings, just understand how sensitive your meter is to those harmonics, and calculating the actual total kilowatts in fundamental plus harmonic, whether it can actually do that or not and how well it does it, is a pretty critical factor in terms of whether you're going to save money or not. So you might want to do some evaluation on how sensitive the meter is, because you may save all these losses inside your facility, and then you get no benefit from it on the billing. Okay, TIF and IT Product. Now, really there's really three things we need to talk about here. And TIF, of course, means telephone influence factor, considers power line harmonic interference with parallel connected communication circuits on the same feeder. But in reality, we have the TIF weighting factor, and I just want you to know that in the 519 standard and in some of the other books and things, you'll find that using the term TIF gets really confused. And so that's why I like to break it down into these three main components. That is the TIF weighting factor, a value that we can calculate using the weighting factors called KBT Product, and another value called the IT Product. Now, the weighting factors. Right out of the IEEE 519 standard, you'll find the weighting factors in a table just like this. And if you plot them, you will get the 1960 curve. And what I did a while back when I was putting together, this is quite a while ago actually, when I was putting together the harmonic notes. And no, I was not putting these harmonic notes together in 1918. So no, I was not doing that. But, or 1935. Actually, I was born in 61, so I would have barely known, or would not have known about the 60 curve. But anyways, whoops, let me go back. So what I did a while back is I researched the different TIF weighting curves. And boy, you know, if you dig around in the old electrical engineering handbooks and things, you'll find some really great content. In fact, I have a paragraph that I read in my harmonics class that I teach. I'll be teaching a full harmonics class, a four-day class at EasyPower World that's coming up in July, I believe. And I have a comment that I read about this. There's an older version of the electrical engineering handbook that has a phenomenal description of TIF, IT Product, KBT Product. It's really, really a good description. But here you can see that over the years and the improvement in audio quality with telephone systems, they changed the weighting factors. So 1918, very narrow frequency band for communicating. Things got a little better in 1930. By 1935, 1941 getting better, 1960 giving us this nice hump here between 2,000 and 4,000 hertz, okay? Which means this is the greatest area of sensitivity. So what the weighting factor for is not only showing the sensitivity of the communication equipment, the bandwidth, the frequency bandwidth, but it's also showing you which harmonics audibly affect people the most. Okay, it's kind of a lumped combination of all those things. It also includes a standard distance, a mutual coupling standard distance between overhead conductors and a communication circuit. So please understand, these are not absolute numbers. that you're going to come out with when you finally calculate IT product and KBT product. They're somewhat relative because you go on a distribution feeder at 13.8 and your current is hundreds of amps, you're going to calculate a fairly low value. You go down to 480 volts where your currents are thousands of amps, you can calculate a really high large number based on where you are. And the IT product is an ampere number, and the KBT product is kV. So just understand that even though there's some numbers, we're going to talk about it just after this slide, but there are some numbers for typical IT product values, you have to really be careful there. You have to really be careful and understand it's really more of a relative thing. So KBT product is very simply, you take the kV at each harmonic, multiply it by the weighting factor at each harmonic, square it, sum them up, and take the square root. And similarly for the IT product, you take the current in amps at each of the harmonics, the TIF weighting factor at each harmonic, you multiply it, square it, and then you sum them all up and take the square root. Similar to like an RMS calculation. So this gives you a total figure that lets you discern what type of an interference level that you have, similar to total harmonic distortion, but it's weighted. It's weighted according to voice, to spacing, to harmonic, to frequency response of the equipment, etc. Now, consider these comments. TIF is not limited in the 519 standard. Please understand, it is not. The standard supplies guidelines and typical values, and let me tell you what the guidelines are like. They're on the next slide, okay? But really, they're more like typical values. And so when I use these, and I've used these in the past, I had a client one time that had a severe communication loss. And basically, what I did was I calculated what the TIF and IT, I built a model, then I calculated what the IT product and the TIF was on the system with that bad condition happening. And then I said, well, I at least want to cut that in half or maybe by a factor of 3 or 4 to reduce the problem. And we ended up putting capacitors strategically located on their distribution system until we got the value dropped. Now, unfortunately, we created a small resonance on the system too, so it was bizarre. We had higher fifth harmonic, and so we were actually exceeding IEEE 519 harmonic limits on the feeder, but we solved the communication circuit problem. So you can see how these things can go back and forth. Now, the values, the last item here, totally dependent upon physical spacing of conductors and communication circuits. So get this. Who cares about IT product and KBT product if there's no communication circuit? Okay? So these values, they're useless on any type of an in-plant feed or any type of an overhead distribution feeder if there's no circuit, if there's no communication circuit on it. The only time we need to consider these two values is when there really is a communication circuit running in parallel so that it mutually couples with the overhead conductors. That's really the key application here. Now, just a little note here. In the 519 table 11.4, they call category 1, 2, 3 for IT product. They say these are guidelines. Okay, that's what the table says. It says these are guidelines. This is what the category 1 guideline says. Literally, levels most unlikely to cause interference, 0 up to 10,000. Levels that might cause interference, 10,000 to 25,000. Levels that probably will cause interference, greater than 25,000. So I think you can see that there's really no limit specified here. Holy cow, you know, unlikely, might, probably, those are words that are very generic, and that was put in there on purpose so that people wouldn't use the values in the 519 standard as limits. So just a quick note for you on that. Now, harmonic bar charts. I really like to use these when I'm looking at spectral content. Most of the time I use them when I'm matching measurements with simulations, that's that second item down there. If you want to see the spectral content on any branch or on any bus, and voltage versus current, or you want to see how a resonance affects the actual distortion profile. That's a really interesting thing, because when you're out in the field collecting measurements, when there's a resonance occurring, it doesn't have the nice resonance plot like you see when you're doing a driving point impedance thing. It kind of looks odd, and you have to, because the harmonics are really going down from the source, and you have to try and look at it with that hat on, try and look at it in that view to see, well, is there really a resonance there? And they're a really visually compact form of harmonics simulation result. You can copy and paste them right into a report. You know, I like to do that as well. Now, there's two ways to view the harmonic bar charts. The first way is when you're in the focus, and I'm going to show you all this, you just click on the equipment that you want to plot, and then you click bar chart. That's all you have to do. It'll do the summation calculation in the background, and then automatically perform the plot on the items that you selected. The next is that you can use the plot channel definitions to set up multiple plots, and you can have up to 9 of them to see the spectral content throughout the system. Now, finally, single point injection. These two items here, the single point injection and the all source current flow. So the single point injection is used to show where currents flow when an injection occurs at a single point in your system at a single frequency. And you can use this to discover like hidden sinks to where the harmonic currents might be flowing. You can discover how a single harmonic affects your entire system, because when you do it, it'll show you flows and voltages on your entire network. And finally, you can uncover facets to the value of total harmonic distortion. And we could add probably 5 more items. I don't remember every single thing that I can do with single point injection, but these are 3 key things that I've used it for in the past. Now, to perform a single point injection, you click on the bus that you desire to inject, and then you just click on the button single point, and it'll just perform it for you. So at the bus that you click on, it's going to inject the current that is specified in the harmonics options control tab, and I'll show you where that is. For the result, the one line will display all voltage magnitudes and angles and all current magnitudes and angles. All right, the all source current flow presents voltages and currents very similar to the last one, but it presents them in the system model, yes, at one frequency, just like the last method, but it includes current injections, the actual harmonic current injections of all of the sources that you've defined. So for instance, if you wanted to see all of the harmonic current flowing at the 5th harmonic from every source in your system, that's how you would do it. You would basically just go up to the all source and click it, and boom, it would perform it. Now, similarly, its setting uses the same single point injection frequency setting in the harmonics options control tab. It's the same one. So if you set that to 5, it's going to do it for both of them. It's going to do a single point injection at the 5th and an all source current flow at the 5th harmonic. So from this simulation, you can discern the effect of any single harmonic, what that effect is having on THD for the entire system. So you can look at one harmonic and see what its impact is, and how harmonic currents at a single frequency accumulate or cancel. That's a really interesting one. Especially if you have a resonance going on, you can see how the harmonic currents are being amplified. And whether harmonic sources are really injecting at a given harmonic or not. So you put in all your data, and with a quick check, you can click on the all source, and you can look at all your sources that you thought had harmonics at this particular frequency, and if it's 0, it's not injecting anything. So that's a quick way to do some debugging. And the all source current flow, similar to the single point, will display voltage magnitudes and angles and current magnitudes and angles. And we can choose per unit or amps. It's right in the harmonic options where you can change your view. So let's look at some examples. Yes. Let me come here and bring my example case up that I built this morning. And my example has a utility source at 115 kV. This is like a utility substation, a 20 MVA transformer at the utility substation. We have a bus, 13.8 kV bus, and it's got a distribution feed to my small industrial facility over here with a 1000 kVA transformer. And in here I've lumped this into one. Let's just call it one big lumped 500 horsepower drive system. And this has a harmonic spectrum defined in it. Then I have a bare capacitor and a harmonic filter tuned at the 5th. On the right side, I have a distribution feeder, 4-aught, running 10 miles, 10 miles, 10 miles, 10 miles, some load being tapped off here. It's got a pole-mounted capacitor bank, another load. Actually, I've got two pole-mounted capacitor banks, one here, one here. And then at the end of the feeder, I have a 500 kVA transformer with a 100 horsepower drive. All right, this is a pulse width modulated drive that has a pretty poor spectral content, basically. So it's producing a lot of harmonics on this feeder. So let's look at, let's do things in the same order that I presented my slides, and that is, let's first look at transformer derating. So if you go into the power flow focus and we solve the system, this is our base case power flow, we can see that I actually have losses turned on here, if you see that, losses. So I have 1.6 kilowatt of losses and that many kVAR losses, and you can see the flow, the voltage is reasonable on my system, and you can see the load being pulled by the drive. If I go into harmonics and I hit the summation button, the default display, I believe in harmonics, shows you total harmonic distortion for the voltage and total harmonic distortion for current. So we can see we have a rather distorted system here, about 7-8%. We're living with it. It's fine for us, and nothing's burning up on us. But with that distortion being produced, and of course the only place it can go is the utility. So what type of heating am I seeing on my transformer? Now, you don't have to click it. I did that just to highlight that, yes, we're going to look at the derating here. Once you've run a summation calculation, all you have to do is press transformer derating. That's this button here. And here it shows you the transformer C57-110 derating. And what that says is I can't load that transformer past 89.9%. All right? And if I do, it's going to begin overheating. So overheating means what? Loss of life, insulation damage, etc. We all know that. I mean, it doesn't matter if you harmonically overheat it or if you fundamentally overheat it. Okay? If it gets hot, it starts to lose its life and create damage. So the harmonic currents through the transformer are basically giving us a condition where we can't put any more than roughly 90% through this transformer. What's the K factor for the same thing? 1.9. And that's how you display it. All you have to do is click on transformer K factor up here, according to UL 1561. So there you go. Derating, K factor. So what if we had derating and someone incorrectly decided to put some power factor correction on here, thinking they were doing us a favor, and we added the power factor correction capacitor on. Because this produces a resonant condition, we see that, oh, we have a high voltage distortion and the derating drops like a rock, which means now you can only put 67%. That's all the heavier you can load that transformer, 67%. Let's take the capacitor off and let's put our nicely tuned harmonic filter on, and we release the capacity in the transformer. Now we can load the transformer fully to 98%. Now, just to let you know, Sid and Vincent, I saw your questions up here, and I'm going to go through my whole presentation and finish it, and then when I get at the end, I'll address any questions that are up here on the question board. So if you just be patient with me, I'll hang on after the presentation is over and answer questions for you. All right, thank you, appreciate it. Okay, so that's derating right on the inside of EasyPower. It's very fast, it's very quick, and transformer K factor. In addition, I didn't mention this in my slides, but we also have a conductor derating. We actually look at cables and their rated ampacity, and then we do the same similar type of computation that's done for the C57-110, and we apply it to cables. The amount of additional losses the cable can take. This particular one is pretty harmonically rich because it's a dedicated cable feeding the drive, and in this case, you really shouldn't put it over 73% of its rated ampacity for the cable. So not only do we do transformers, but we have conductors as well. Okay, so that's derating and K factor on the one line. What about losses? That's this button right here. Okay, so you click on losses, and what do we see here? We see 3.23 kilowatts of losses in the transformer at this point. Now this is fundamental plus harmonic. Let's take our harmonic filter off, and we see, oh, very interesting. I think this fifth filter was pushing bars back, and that's why the fundamental losses go up. So that's a really interesting thing. Think about that. So have to design your filters correct, you know. In this case, I might have been pumping bars back through here, increasing I squared R losses, depending on how big the filter was. If I have a bare capacitor bank, whoa, goes up significantly because of the harmonic distortion. So you can see the losses, and you'll notice that they're fairly small. And if you remember, when we were back in power flow, the fundamental losses are 1.6. Harmonics, with the resonance, we're at 2.4. Without it, we're 1.7. So under this standard condition here, without any resonance or filtering going on, you find basically that the harmonic losses are kind of a small portion here. And that's what I was trying to get to under, that I was telling you earlier. Even under heavily distorted conditions. Okay, I have a remark here that the audio and video stopped. Is that true for everyone, or is it okay? Oh, okay. There's your remark from Roger Brown. Better, it restarted. Okay, thank you very much for the feedback. It must have been something with the webinar software. Great, thank you. All right, so so for losses, this is where you can get them. And when I get done with all of the one-line presentation, I'll show you how you can get things out in text reports as well. And that's how we get the losses out. Again, you run a summation, and then you can show any of the items in here for the one-line display. Now, TIF and IT product on a feeder. Let's look at our feeder over here. And of course, we're putting losses out right now, but to see IT product and KBT product, you just click on these two. And you'll notice it will displace these two that are displaying on the branch current. You know, the THD number will be replaced with IT product, and the bus voltage THD will be replaced with the KBT product. All right, so what do we see here? Yes, let's look at the numbers and look at they're different depending on what end of the line you're on. And the reason why is because the transmission line has charging, and it can create interesting small resonant conditions just even along the line. And so that's why these numbers are not necessarily exactly the same. And this one includes a loading current factor. This one does not. So this one's going to be more harmonically rich. This one is getting kind of diluted a little bit because of this additional load current that's on here. And so again, IT, VT, notice that they're kind of relative numbers, okay? We're up on a 13.8 kV feeder, and again, my suggestion is look at the values in a relative sense for the severe problem. Model it, match the voltage THD on your model, and then look at the kV T product and the IT product, and then start mitigating. For instance, what would happen if I switched on this capacitor bank? It dropped to 485. Not much of a drop here at this main area, but boy, here it dropped significantly, didn't it? Let's see if I add another capacitor bank on. There we go. And so you can get instantaneous feedback on the one line just by opening and closing breakers to see how your IT product and your KBT product change. And we put both these caps on here and we've reduced it. Now, we could have created a problematic resonance at the same time, so you may want to go back and look at the voltage distortion. That's not too bad. 3, 5, that's definitely over the 519, definitely over the 519, 7 and 8% here. But what was it? See, look at, we were solving an IT KBT product over 10, but boy, this one cap up here kind of lowered the voltage distortion a little bit. So again, it's your system. It's going to respond depending on what you have in it, the amount of capacitance balancing with the amount of inductance in the system. We'll simulate it at each of the harmonics. We'll apply the weighting factors for you, and then you can begin mitigating efforts, placing capacitance in locations, trying to absorb some of the higher frequencies, maybe even putting harmonic filters on. For distribution feeders, I've discovered harmonic filters typically don't work well. Just a carefully placed capacitor bank is one of the best alternatives that I've seen. Okay, bar charts. Now, let's go back to our small industrial over here. And what if I wanted to see the actual spectral content that my drive, let's say I want to put it into a report. If you click on this branch feeding the drive and say bar chart, voila, we have the spectral content being injected. This is a 6-pulse characteristic, right? 6-pulse characteristic. We've probably seen this before. 5, 7, 11, 13, etc. And we have a nice bar chart of it, so we can see that. Now, I have the units set for amps right now. What if we wanted to look at the amount coming from here, the amount going to the transformer, the amount sinking into a filter, a capacitor, and then possibly the amount sinking into filter. Now, these are open right now, so they're going to produce 0, but at least I have my plot prepared, you know. I just click on bar chart. And I'm going to move these around a little bit, okay, just so I can see it. I can get some, some real-time update here on the plotting. So what would happen if I were to, for instance, resonate the system? Very interesting. Look at the change in the content when I resonated. The 7th is significantly higher, so that looks like my resonance is probably somewhere around the 7th because it's the one that gets, look at that, it's the one that's getting notched up significantly higher than all the others where they were. Now, what would happen if I had a harmonic filter on? It's a 5th harmonic filter, and we notice that the transformer, the red, is way down. Why? Because it's coming, the cable feeding the drive, it's high there, and then the purple is what's going into the filter, and it's high there. But what's being released out to the utility has dropped significantly. And we notice that even though it's a 5th harmonic filter, we get significant amount of absorption at 7, 11, 13. Look at that. It's almost half of the amount that's going out in the filter. Actually, it's over half. The filter, here's what's going out from the source, and here's what's going into the filter at the 7th harmonic. So not only did we fix a resonant problem by putting on the right kind of filter, but then we absorbed even 7, 11, and 13. Okay, so that's how you can get a bar chart just by clicking on some components. Now, let's say we wanted to look at the voltage distortion. You just click on the bus, you click the bar chart, and it didn't go. Let's clear the bar chart. I have to do that first. Click on this, and then click on bar chart. And now we have the voltage. So we can see what the voltage profile looks like. Normally, look at it, doesn't go down quite as much. And the reason why is because the reactance of the system is going up with frequency. So it's kind of, even though the current's going down, 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 you reach a point to where the voltage distortion continues almost linearly because of the increase in reactance of the system. If we have a resonance, we can see where the resonance is. It's somewhere around here because the seventh is significantly increased. And if we put on our harmonic filter, we see what the voltage distortion profile looks like. Again, we keep down the 5 and the 7 significantly lower than they were before. So that's how you can use bar charts in a real quick fashion. Another way that you can do it is, let's close this one. You can use plot definitions. So you click on the plot. See, I'm going to close it again. I'll close it for you and start over again. So define plots. And now you can click what you want to monitor. So let's say we wanted to monitor this. I'm holding the shift key. This, this, this. And then I say add. Now it added it to plot 1. I could go to plot 2. You have 9 of them. Now we can put something else. Let's say I want to look at the voltage distortion here and here. Okay? Very good. Now let's close. All we have to do is click on bar chart. And notice the auto plot doesn't have anything. The auto plot is created when you click on a few items and then hit bar chart. But we didn't do that. We just hit bar chart without clicking on any item. And our results are only presented now in plot 1 and plot 2. So that shows you how you can get a whole set of plots across your system with the Harmonics module looking at spectral content. I think that's a really powerful feature in the package. Okay, so we've looked at bar charts. Now, the 2 final solution methods for analysis, and that is the single point current flow and the all source current flow. Let me maximize this again. And let's look at the single point. So what we need to do here is first pick a bus where we want to inject. Now, an obvious logical location would be at the drive, this M1 down here. So we'll pick this bus and we'll click on, now if you don't do that and you click on single point, you'll get a message saying you must select one bus as the injection bus. And while I'm at it, let's just look at the harmonic options real quick. The harmonic options here say I'm going to analyze at the 5th harmonic and I'm going to inject at 1 per unit, okay, for my scan or my single point injection. Very good. So let's select this bus and do single point. Now, because I had my display options for the 1 line here, control, down, are they here? Nope, 1 line. 1 line output, display, bus voltage per unit, branch current per unit on system base. I can see that it is indeed a 1 per unit current injection. Now, we have a 5th harmonic filter on. Very interesting. I'm injecting 1 per unit current. 92.1% of it is being dumped into the filter, and 8.1% is still going out to the utility at the 5th harmonic. Okay, what if I were to open this? All of my 5th harmonic current from this single point would go out to the utility through the transformer. Okay, what would happen if I resonated with this capacitor here? 1, but we're at the 5th harmonic now. We're at the 5th harmonic, okay. 1 per unit is on the base of the system. So it's 1 per unit current, all right? 1 per unit wherever I happen to be. So the base MVA for my example is 10 MVA, and so you calculate base current, you know. I could put this in amps and you'd see it come out in amps. I like to look at it in per unit so I can see this breakdown. So 1 per unit goes over here. There's 67% going in here. But it's doing something funky because it's not adding to 1 very easily. And that's because these are two out of phase with each other. Now, we're at the 5th, so it's really hard to see what's happening here. So one of the methods I spoke of in my first Harmonics webinar was the scan, the frequency scan. I'm going to do that here. I'm going to double click on bus 6. And what I notice here, if I zoom in, is that my resonance is around the 8th harmonic. If I put my cursor on here, it's around 7.9 to the 8th harmonic. Okay, that's where the resonance is really happening. I'm going to uncheck this now. I'm going to close this frequency scan. So if I were to go to the harmonic options under the control tab and set this to 8, 7.9 or 8 in that range, and hit OK, and then do a single point injection down here, you will discover that you have 1 per unit current being delivered or forced into the system. You have 19.978 per unit in the capacitor and 19.3% going up to the grid. That, my friends, is a classic tank circuit. That's what happens. You're only putting 1 into it, and the 2 legs involved in the resonance grow to extremely high amounts, but they're phased 180 degrees out of phase, so that when you subtract them, you get 1. So this is a very nice way, the single point current flow, where you can show what's really happening in a circuit at a particular frequency of your choice. And the all source current flow is very similar to it, but it allows you to inject from all sources. So let's set this back to 5. This is now going to be ignored with the all source, and let's click on all source. Now, these numbers are in per unit, and so what that tells me is, now, by the way, the per unit current, the base current for this part of the system at 40 volts is like 1200 some amperes. It's a really high number. So these numbers look really small because they're being put on that base. But if we go to harmonic options, go to the 1-line output, and change this to amps, we'll now see what we're injecting in amperes. Let's undo this. And what we see, if we have no resonance and no 5th harmonic filter, that 96 amps of 5th harmonic current, 96 amps of 5th harmonic current is escaping out to the utility grid through the transformer windings now. It obviously gets scaled down because the voltage went higher. It goes down to 3.3 amps, and it accumulates on this bus and then is served by the main feeder at the utility distribution substation. So the other amount of 5th harmonic is being produced by this drive down here. It's got 48 amps of 5th harmonic, and it flows up through the system. And it goes through the conversion of the turns ratio through the transformer and finally makes it up here and sums. Now, these sum linearly mostly because I specified my injections. If I go back to database focus, specified my injections at a current angle of 0 for the entire spectral content. And so there'll be some amount of phasing occurring in the system, but all the current angles are 0, so each of the harmonics should pretty much add linearly in the system. Okay, so that's the all source current flow. Show that again here. So we can see what happens to this 5th harmonic current when I have a 5th harmonic filter on. We can see that most of the drive current is being sunk into the filter at the 5th harmonic current, but not much is happening up here. This is all going out onto the system, this 1.678 amps. What would happen if I were to close this capacitor? We start getting some interaction at the fifth harmonic. We close another one. We can see another slight interaction. If these were bigger and they were resonating down towards the fifth, you might see it pick up into a resonant condition. Okay, so that's the all source. So that's wrapped up the points that I had on my slides. And what I would like to do is just one last thing, show you that you can see these in report form under Harmonic Reports. The losses are reported here under the loss report. K-duty transformer derating here. Conductor derating. VTHD root sum square VTIF, which is the KBT product. THD root sum square of current, IT product and losses on the branch. And if you hit OK, and we go to window, I think I just ran an all source. To get that report, it has to be done through summation. And here we go. There's the bus summation. There's a VTIF if you want to see it in a tabular form with the THD all in one report. There's the branch summation report. There's the IT product and ITHD. There's some loss values there as well. But the main ones that we're interested in are in this branch loss report, where we can see the transmission lines and their losses and the transformers and their losses. There's the derating report. There's our transformer K-duty and our capability. We must have had that fifth harmonic filter on because our capability is here. Yep, if we would have changed the breaker to have the higher harmonic current flowing through it, you would have seen this down at 89.9%. And finally, the conductor derating report. And that shows that one conductor that we had that's running a tad bit hot. So that's it for today. That was our discussion on some advanced harmonics topics. And I want to thank you all very much for attending. And hopefully we'll have another harmonics webinar with some more topics. Obviously, if you go back here, you'll see there's still more things that we could address and talk about. Different forms of why we would have such a thing called V-sum, for instance. And that has something to do with a capacitor rating, where we want to do a summation of harmonic currents for the capacitor standard. I think it's capacitor standard 8 that you look at peak sum for looking at voltage stress on capacitors. So we have a number of topics we could talk about in the future again on harmonics, but that wraps up this one for today. Thank you very much. Have a good day.